Hello and welcome to this lecture of dynamics of machine. In this lecture we are primarily going to focus about the turning movement diagram of a steam engine. In my previous lecture I have explained that how we can develop a turning movement diagram. So today we are going to focus mainly on the turning movement diagram of a steam engine. I'll start with the concept of what is a turning movement diagram. So we all know that when in the engine, when forces applied on the piston, these forces are not constant. So for one complete revolution of the crank, the torque on the crankshaft is not constant. If I am representing the variation of the torque with respect to the angle of the rotation of the crankshaft, the diagram is particularly known as the turning moment diagram. Now let's understand what is a steam engine, how a steam engine work, and then we will make the turning moment diagram of a steam engine. So here I am showing the single acting steam engine. This is normally looks like a 4-stroke engine, but what is basically when we see the operation of a steam engine, what happened that this is the geometry of the steam engine. Here we are having a cylinder, there is a piston connected with the connecting rod and then crank. There are two valves, one is the inlet valve, another one is the outlet valve. So what happens, suppose my piston is initially at this position. Now at this condition, this outlet valve will be in the closed state and the fresh steam will come through this inlet valve. When the fresh steam will come here, there will be certain forces because of the inlet of the steam, and because of these forces the piston will move towards this side. When the piston is at its extreme position, the connecting rod and crank will be in a straight line. As the piston will start moving in this direction, and I am assuming that the crank is rotating in this direction, what will happen? As the piston will move toward this side, there will be rotation of the crank. In the second diagram, I am explaining an intermediate condition when the piston will travel certain distance, so there is a rotation of the crank, and I am assuming that this rotation is theta. After that, what will happen? This process will continue till the piston will reach to its next extreme position. So now here I am representing the final state of my piston. When the piston will be at this extreme position, this is the orientation of my connecting rod and the orientation of the crank. When piston will reach here, again it will move to its original position. While it will go from this extreme position to the other extreme position, whatever exhaust steam remains in the chamber will go out through this exhaust valve. During this period, when piston will move from its right position to the left extreme position, the inlet valve will be in the closed state. So in this fashion, again when piston will reach here, the inlet valve will get open and fresh steam will come inside the chamber and the process will repeat. So here we can see that for a half rotation of the crank there is a power to the system, but for remaining half rotation there is no power generation, or there is no steam which will give power to my system. Instead of that, what happens, I have to use, or the system has to use its energy to move the piston from right extreme position to the left extreme position. That means during this period there is a negative torque on the crankshaft, because crankshaft has to work, and that work basically comes from the flywheel. But for this motion, when there is a steam inside the chamber, the system receives certain energy because of the steam. Now if I will see a double acting steam engine, in case of a double acting steam engine, what happens, suppose this is my cylinder. Here we have two inlet valves, two outlet valve, and what happens, suppose my piston is initially here, the fresh steam will come from this side. It will apply certain force to my piston, so my piston will move from its left position to the right position. When it will move in this direction, I'm explaining here that this is the initial condition of my piston. This valve is open, this inlet valve is closed, this exhaust valve is closed, and the other exhaust valve is open, because whatever remaining steam from the previous cycle we will exhaust during this motion. So So let's focus that this inlet valve is open, fresh steam will come from here, it will apply certain force to the piston. Because of that, the piston will move here. And if you will compare the geometry of the single stroke, single acting and double acting steam, you can see here that the connecting rod is directly connected to the piston, but here because I need a closed chamber, because steam will come both sides of the piston, this will not be opened like this. So there is a additional member which we call piston rod, and piston rod is then connected to the connecting rod and crank. So here when piston will move from this extreme position to right extreme position, there is a power generation. When piston will reach to this position, this valve will get closed, these two valves will get closed, and now fresh steam will come from this inlet valve. So again my piston will receive certain energy because of the steam. Whatever exhausted steam is here, when the piston will move from here to here, exhaust steam will go out, and again my piston will reach to this position. So here I can observe that when my piston is moving or when my crank is rotating half revolution, there is a power generation because of intake of steam from this side. For remaining half rotation, there is a power generation or there is a energy supply to the system because now fresh steam insert into the system through this valve. So in case of double acting steam engine, what is happening? For each stroke of my piston, there is a power input to the system, but when I will see the single acting, for half rotation or for one stroke there is a power input, but for remaining half rotation or remaining stroke there is no power generation. So we call it single acting and we call it double acting. Now if I am interested to make the turning moment diagram of a single acting steam engine, so to understand the turning moment diagram, here I am representing the expression of the torque on the crank. The torque on the crank can be represented by this formula, where F is the piston effort, R is the length of the crank, theta is the angular rotation of my crank, N is the ratio of the length of connecting rod to the crank. And how I have developed this formula, this we have already covered in our lecture when we discussed the forces on the engine component. Here I am just giving an idea that how this formula developed. When there is a pressure on the piston, the piston will apply certain forces to the crank. That force I am representing here by Fc. That Fc can be broken into two components, one perpendicular to the crank and one along the crank. So that perpendicular component, when it will multiply with the length of the crank, it will give a torque, and that torque further can be, when I will put this Fc value and then I'm again more values, I will get finally this formula. If you are interested, you can see my other video. This F is the piston effort, which will be basically combination of two forces. One is the forces because of this steam or gases, another one is the inertia force. So my piston effort will be pressure into area because of these gases and the inertia force. So in case of single acting steam, when I am talking about its motion from left to right condition, the gas pressure will exist as well as inertia will exist. But when I will talk about the motion from right to left extreme position, this Fg will become 0 and only F inertia will exist. And you can see here that this I am assuming that negative. So when piston is moving from right to left position, this torque will be negative. So if you are using the mathematical expression, you can also get the negative and positive torque value. But for physical understanding, you should know that while piston is moving from this to from left to right position, there is a generation of energy because of the steam. But when it is moving from right to left position, it has to work within, generate work from within the system. That is basically come from the flywheel, and the torque is negative here. So now if I am interested to make the turning moment diagram of my system, I know that this y-axis is representing the torque and the x-axis is representing the rotation of the crank or the crankshaft. So for half rotation, when the piston is moving from left position to the right position and my crank is rotating an angle of 180 degree, so this pi angle, for this pi angle I am assuming that as the steam will come inside the chamber, initially the force on the piston will increase. Up to certain distance the force will increase, and after that the steam exhaust and the force will reduce. So for one stroke, when the crank is moving from 0 degree angle to 180 degree angle, initially the force will increase. As the force will increase, the force on the connecting rod will increase, and ultimately torque on the crank will increase. So I am representing my torque using this particular curve. You may think that why not the triangular shape or square shape or round shape. So don't worry, this shape either will be given to you, or the equation of this curve will be given to you, or it will be given that you can assume that it will be a triangle. Here I am just giving a concept. So I am assuming that my torque will first increase and then it will decrease. I am not saying that it will be exactly at the 45 degree or 90 degree there will be maximum torque, but you can assume that in between this position initially the force will increase and after that it will decrease. Beyond that, my piston will be here now, and I have to give certain work to the piston so that it will go back to its original position. That work will come from the system and negative torque, so I can represent it with a value that would be my negative torque. So my work done will be the area of this T theta diagram, and this is the turning moment diagram for a single acting steam engine. If I will repeat it again, what will happen? Piston will come here, so there will be again generation of work, or this area representing the work generated because of the steam, and again there will be a negative work. Sometime it is given that the work done during the return motion of the piston can be 0. So my diagram will have simply one peak, then straight line, then again second peak and the straight line. So and why we considered it? Because the work done required to move the piston to its original position is very less compared to the work generated because of the pressure of the steam. Now if I will assume, I can consider that this is one complete cycle. For that purpose, what will happen? Piston will move from here to here, and again that will go back to its original position. After that, the initial position will repeat itself. So I can consider that for one rotation this is my cycle. And if I am interested to find the mean torque, my mean torque will be the area of this curve, area of, suppose this is A, B, C, D and E. So area of A, B, C, D and E divided by the 2 pi value. So when I will calculate this value, this can be this is a mean torque which can be represented by a straight line. So I can represent that the cross section area of this curve, this square body, which can be represented by T mean into 2 pi, will be equal to this area of this curve, which is A, B, C, D, E. So in this way we can calculate the mean torque. And what is the physical significance of this mean torque? So the physical significance of this mean torque is that this is the basic output of your engine. This part we have already discussed in our previous lecture, so here I am not going to detail it. Basically what happens, we are using one engine to generate certain power so that you can run a particular system. For example, you want to run one automobile using the engine. So whatever torque is required for the automobile can be considered as the mean torque. And why it is so? Because there is a flywheel. Flywheel ultimately supplies certain power or certain torque to your desired system, and that torque should be a constant torque so that there will not be any fluctuation, or it should be a constant torque. So for that purpose, that T mean generated because from the flywheel and the flywheel receive a variable torque through the engine. So ultimately the work of the flywheel is to make balance or receive a variable energy from the engine and deliver constant energy. And during that cycle you can see here that this is the basic output from the flywheel. So what happens actually? If I will consider this point, the desired output for this instant should be this value, but actual generation for this value is this value. So this is the depreciation that is supplied when we are having a surplus value. So if I will break this system into 2 half cycles, for first half cycle there is a requirement of this much energy to my external system, but there is a generation of energy which is more than the required value. So the surplus value basically stored in the flywheel, and for next half cycle, when my requirement means there is a negative requirement, means we required work from the system itself. That work as well as whatever required to run the external system is supplied through this surplus value. So if I will see the speed of engine, what will happen to the speed of engine? During this process there is a surplus energy to the system, so the speed of the engine will increase or the speed of the flywheel will increase. For this motion there is a negative work or work has to be drawn from the flywheel, so the speed of the flywheel will decrease. So I can see here that for this position there will be minimum energy, then the external work will be supplied to the flywheel, so at this point the maximum energy in the system, so the speed of the engine will be maximum at this point. We will see this in detail when we will talk about the fluctuation of the speed in the flywheel. Currently I am just explaining that how you can make the turning moment diagram of steam engine. So if I am interested to make the turning moment diagram of a double acting steam engine, in case of double acting steam engine, what will happen? I know that for one half cycle there is a power generation, and for remaining half cycle there is again a power generation. So I can make a diagram that for first half rotation there is a power generation. Similarly for the second half rotation there is a power generation. I am ignoring the work required to move the piston from right to left, while the piston will force these exhaust gases to move out. So certain energy will require to force these exhaust gases to go out, but if I will ignore this work, for each half rotation I am getting power. So for in case of a double acting steam engine, this will be the shape of my turning moment diagram. If I will make so in case of a double acting steam engine, repetition will be after half rotation. So instead of taking one complete rotation, I can assume that my cycle completed in half rotation. So if I will calculate the mean torque, I can consider only this area. Suppose this is A, B and C. So my mean torque will be area ABC divided by the pi value. Or if I am interested to calculate the mean torque for one complete rotation, then I have to calculate this complete area. So my mean torque may be A, B, C, D, E divided by 2 pi. So in case of a single acting steam engine, if you are interested to calculate the mean torque, you have to consider this complete area, because this is the cycle. After that it will repeat, but in case of a double acting steam engine, for every half cycle there is a repetition, so I can assume that one cycle completed in half rotation of my crane. Here also if I will calculate the mean torque, and if I will make the mean torque here, whatever area covered by this is going to balance by the total area. So if you will see the exact diagram in this way, the exact diagram will look like this, and this would be my mean torque. So whatever additional is required for this zone, basically supplied by the surplus value. So ultimately for one half rotation, my torque will vary, and this variation is just minimized by using a flywheel. I have already discussed why the flywheel should have high moment of inertia and how the flywheel minimize the fluctuation of the speed within the cycle. You can see this in my previous video. So I'm just briefing this lecture that in this lecture we have studied the turning moment diagram of a steam engine. We have seen the working of a single acting steam engine, then we have seen the working of the double acting steam engine, then we have seen the turning moment diagram for the single acting steam engine, and here is the turning moment diagram for a double acting steam engine. Thank you.